Databases are the lifeblood of modern businesses. They store vast amounts of information, from customer details to financial records and inventory data. Behind the scenes, these databases rely on a robust storage infrastructure to manage and protect this critical data. Oracle Database, a leading relational database management system, employs a sophisticated storage architecture built upon the concept of tablespaces. Tablespaces are the fundamental building blocks of Oracle's physical storage. They provide a logical container for storing database objects, such as tables, indexes, and stored procedures. Understanding tablespaces is crucial for database administrators and developers alike. It allows them to efficiently organize data, optimize performance, and ensure the scalability and reliability of their databases. This essay delves into the world of Oracle tablespaces, exploring their various types, their role in the storage hierarchy, and best practices for their management. We'll start by examining the foundation of Oracle's storage hierarchy, understanding how data is organized from the physical disk all the way up to the database schema. Then we'll explore the different types of tablespaces, each with its unique purpose and characteristics. Through real-world examples, we will illustrate how these tablespaces are used to manage different aspects of the database. Finally, we'll discuss the critical importance of managing tablespaces effectively, outlining best practices for allocating storage, monitoring performance, and ensuring optimal database efficiency. By the end of this essay, you should have a solid grasp of Oracle tablespaces and be well equipped to manage them effectively in your own database environments. Oracle's storage hierarchy is like a well-organized library. At the bottom level, we have physical disk drives, the bookshelves that hold everything. These are organized into operating system blocks, the individual shelves on the bookshelf. Oracle groups these blocks into larger units called extents, representing a collection of books on a particular topic. Multiple extents are then combined to form a segment, a dedicated section for a specific type of data, like a shelf for fiction novels. For instance, a table would have its own segment, as would an index. These segments are then stored within tablespaces, akin to separate rooms in the library for different genres. Each tablespace can house multiple segments, providing a logical grouping for related data. Finally, at the top level, we have the Oracle database itself, the entire library. This hierarchy allows for efficient data management, enabling the database to quickly locate and retrieve the information it needs. By understanding this structure, we can better appreciate the role of tablespaces in organizing and managing data within the Oracle database. The system tablespace is the central hub of the Oracle database. It's the first one created when you install Oracle, and it's absolutely essential for the database to function. Think of it as the library's control room, containing vital information about the entire database structure. The system tablespace stores the data dictionary, which is like a master catalog of all database objects. This dictionary contains metadata about tables, indexes, users, privileges, and other critical components. Without the system tablespace, the database wouldn't know what objects it holds or how they are connected. It also stores critical internal structures and administrative data, ensuring the smooth operation of the database. Due to its critical role, the system tablespace requires special attention and careful management. It's generally recommended to keep the system tablespace separate from other data, ensuring its performance is not impacted by other database operations. Regular monitoring of the system tablespace is crucial to ensure it has sufficient free space and that its performance remains optimal. User tablespaces are where the bulk of your application data resides. These are the general-purpose storage areas for tables, indexes, and other objects related to your specific applications. Think of them as the various subject-specific rooms in our library analogy, each dedicated to a different area of knowledge. For example, you might have a user tablespace for your customer relationship management, CRM application, another for your financial data, and yet another for your inventory management system. Each user tablespace provides a logical container for grouping related data, making it easier to manage and control access to specific information. This separation also enhances security, as you can grant different privileges to users based on the tablespaces they need access to. Creating multiple user tablespaces allows you to tailor storage parameters and performance optimizations to the specific needs of each application. You can control the storage capacity, allocate resources, and implement backup and recovery strategies specific to each user tablespace, ensuring optimal performance and data protection for your critical applications. Section 5. Temporary tablespaces, scratchpad for complex operations. Imagine you're working on a complex puzzle in our library analogy. You need a temporary space to lay out the pieces, sort them, and try different combinations. That's essentially what a temporary tablespace does for the database. It provides a dedicated area for temporary data storage used during complex operations, such as sorting large datasets, joining tables, or creating indexes. When the database needs to perform these operations, it allocates space within the temporary tablespace to store intermediate results. Once the operation is complete, the temporary data is discarded, freeing up the space for other operations. This temporary storage is crucial for preventing these complex operations from impacting the performance of the main database. Using temporary tablespaces effectively can significantly enhance database performance. By segregating temporary data from permanent data, you prevent contention for resources and ensure that critical database operations are not slowed down by temporary data processing. This results in faster query execution, improved application responsiveness, and a smoother user experience overall. Section 6. Undo tablespace, a safety net for transactions. In the realm of databases, transactions are sequences of operations that must be treated as a single unit. Either all the operations within a transaction are completed successfully, or none of them are. This ensures data integrity and consistency. The undo tablespace acts as a safety net for these transactions, providing a mechanism to roll back changes if something goes wrong. It stores undo data, which is essentially a before image of the data before any changes were made. If a transaction fails or is intentionally rolled back, the database can use this undo data to revert the affected data to its original state. This ensures data consistency and prevents incomplete or erroneous transactions from corrupting the database. The undo tablespace plays a critical role in data recovery as well. If the database crashes unexpectedly, the undo data can be used to reverse any uncommitted transactions, restoring the database to a consistent state. Proper management of the undo tablespace is essential for ensuring data integrity, facilitating efficient transaction processing, and enabling reliable database recovery. Section 7. Index, tablespaces, accelerating data retrieval. Imagine searching for a specific book in a vast library without a catalog. It would be a daunting task. Indexes in a database are like the library catalog, providing a quick and efficient way to locate specific data. Index tablespaces are dedicated storage areas for these indexes, which are structures that speed up data retrieval. Indexes work by creating a sorted copy of specific columns in a table, along with pointers to the actual data rows. When you query the database engine can use the index to quickly locate the relevant rows without having to scan the entire table. This is especially important for large tables with millions of records. By storing indexes in dedicated index tablespaces, you can optimize their performance and manage them independently. This allows for greater flexibility in tuning and configuring storage parameters specifically for indexes, leading to faster query execution, improved application responsiveness, and a more efficient database overall. Section 8. Segment space management, automatic versus manual. When managing tablespaces, you have the choice of how space is allocated to segments within them. Oracle offers two main approaches: automatic segment space management, or ASSM, and manual segment space management, or MSSM. ASSM, as the name suggests, automates the process. The database engine dynamically allocates extents to segments as needed, simplifying management and reducing the need for manual intervention. MSSM, on the other hand, gives you granular control over how extents are allocated. You can define the size of extents, control the number of extents a segment can have, and manage free space within the tablespace. This level of control can be beneficial in specific scenarios where you need to fine-tune storage allocation for performance optimization. The choice between ASSM and MSSM depends on your specific needs and the complexity of your database environment. ASSM is generally recommended for most cases due to its simplicity and efficiency. However, MSSM might be preferable in situations where you require precise control over storage allocation for performance-critical applications or to address specific storage constraints. Section 9. Best Practices. Optimizing tablespace usage. Managing tablespaces effectively is crucial for database performance and efficiency. Here are some best practices to keep in mind. First, plan your tablespace allocation carefully, considering the expected growth of your data and the specific needs of your applications. Avoid creating unnecessarily large tablespaces, as this can lead to wasted storage space. Second, monitor tablespace usage regularly, tracking free space, fragmentation levels, and performance metrics. Identify potential bottlenecks early on and take corrective action to prevent performance degradation. Third, consider implementing automated space management tasks, such as resizing tablespaces or adding data files, to streamline administration and ensure sufficient storage capacity. Finally, optimize storage parameters for your tablespaces, such as block size and extent size, to align with the characteristics of your data and the workload of your applications. By following these best practices, you can ensure your tablespaces are used efficiently, maximizing database performance and minimizing storage costs. Section 10. Conclusion. Mastering tablespaces for peak performance. Tablespaces are the foundation of Oracle's storage architecture, playing a critical role in organizing data, optimizing performance, and ensuring the scalability and reliability of the database. From the central system tablespace to the application-specific user tablespaces, each type serves a unique purpose in managing different aspects of data storage and retrieval. Understanding the different types of tablespaces, their characteristics, and how they interact within the storage hierarchy is essential for database administrators and developers. By mastering the concepts of tablespace management, you can ensure your database runs efficiently, providing optimal performance for your applications and ensuring the integrity and availability of your critical data. Effective tablespace management involves careful planning, regular monitoring, and the implementation of best practices for storage allocation and performance optimization. By adopting a proactive approach to tablespace management, you can avoid potential bottlenecks, minimize storage costs, and maximize the performance of your Oracle database, ensuring it remains a robust and reliable platform for your business-critical applications.